So at the end of our last class meeting, we were talking about positive feedback circuits, and I kind of ran out of time. I didn't kind of ran out of time, I just ran out of time. So I went ahead and set a astable multi-vibrator circuit up in LT Spice just so that you could kind of see how the circuit is implemented. I'll write this stuff down here in a minute. We'll get into a little bit of the math. But effectively, this circuit to me is pretty darn interesting because it literally does not have an input. So this is a situation that I talked about in the class where essentially our feedback factor times our open loop gain is intentionally set to be equal to 1 so that we get oscillations with effectively no input voltage whatsoever. Now, because I'm using ideal components, I did have to give my system a little bit of a push. So I gave my capacitor an initial voltage of 1 millivolt, which isn't an unreasonable amount of thermal energy stored in our capacitor. We all saw using our multimeters and stuff like that, that we usually had a couple of millivolts of variance when we were measuring voltages across elements just due to thermal noise. So this is a realistic amount of energy that might be stored by a capacitor connected to a circuit. And within about 3.5 milliseconds, our transient has died out enough to where we just get our switching. So if we look at this circuit here, so we're going to start from a place where our output voltage is at VCC high, which in turn means that our reference voltage in this case is going to be exactly 1/2 of VCC high because it's split over that simple voltage divider network on the right-hand side right here, right? So if we have 10, if we have 5 volts here, and then there are 2 identical resistors on its path towards ground, the reference voltage is just the voltage drop over this resistor R2, which is just going to be half a VCC plus. We could play around with those values of R1 and R2, and I'll show you where the math for that is. So effectively, what we've got here is our capacitor voltage is always chasing our reference voltage at that node. As soon as our capacitor voltage catches up to our reference voltage, our output actually switches because our differential voltage is just the difference between VC and VREF. So and we've got a positive feedback situation, so as soon as it hits and even ever so slightly exceeds it, it's going to wind up flipping the sign on that reference voltage, and then the capacitor voltage is going to slowly chase that guy to the next step because we know it takes time for capacitors to charge and discharge. So that's all that's going on in this circuit is the capacitor voltage is constantly chasing the reference voltage, and the reference voltage is set by whatever V out is. So either VCC plus or VCC minus applied across that simple voltage divider network. I designed this circuit specifically to have oscillations at a frequency of 1 kilohertz. And so we can kind of see that here. So I have my first marker right here, where my output voltage has switched high after my transient died out. And we can see that that horizontal axis occurs at 4.059 milliseconds. And then I have my marker 2 set here, the next succeeding positive peak, and that's occurring at 5.072 milliseconds. So if I take the difference of those guys, I'm getting 1.01 milliseconds, which is happening because I have some rounding error by only putting my capacitor out to be 3 digits. So now let's redraw this circuit on our notes and then talk about how we could design a circuit like this for a specific frequency. Okay. So these are going to be added to the end of the positive feedback notes that are currently on canvas, so I'll wind up taking those down and re-uploading these since this is still talking about positive feedback circuits, okay? So here on our very last page, if I can find my notes, we're going to talk about our op amp multi-vibrator circuit. We're not going to get into too much of the weeds about analysis because we've already conceptually seen how this guy works. So instead, I'm just going to draw our circuit here. So here is a resistor that I'm just calling R. And this guy, along with the capacitor C, is largely responsible for setting the overall timing of the system. Okay. Now I'm drawing my op amp. I'm choosing to put the inverting terminal on top, but I'll still label my supply voltages as VCC plus on top and VCC minus on bottom. My positive feedback path is going to be from my non-inverting input terminal out to that voltage divider network. So here's my resistor R1. Here's my resistor R2. And then I'm also going to have negative feedback in this circuit. So that resistor R across the top is connected between the non-inverting input terminal and our output terminal. So that's providing negative feedback. The effects of positive feedback are essentially canceled out by this guy because positive feedback behaves so strongly. Down that left-hand branch, I'm going to have my capacitor C, like so. And then I'm going to apply my ground node here at the bottom, okay? So the frequency that my multi-vibrator circuit will oscillate at is going to be given by 1 over 2 times R times C. So R times C is just the time constant for a generic RC circuit. So effectively, we have one time constant to allow it to increase, one time constant to allow it to decrease before it starts over. And then we're going to have the natural log of 1 plus beta over 1 minus beta, where beta is just the voltage divider ratio for R1 and R2. So that'll be simply R2 over R1 plus R2. So choosing those two resistors, R1 and R2, is what allows us to essentially fine tune our oscillator because we can't ever get like exact value capacitors and resistors to hit specifically a very exact signal. So we have to fine tune it with those two resistors R1 and R2. So this is all of the math behind how you would design an op-amp multi-vibrator circuit to hit some specific frequency. Really, you would just choose an RC value that's going to be effectively half of the period of your desired signal, and then you'd fine tune things with R1 and R2 to tune it into the exact frequency that you're interested in. Okay. So there is your astable multi-vibrator circuit and its constituent equations. All right, so now let's talk about negative feedback circuits. Actually, let me go back there and save that guy. Yes. So without re-deriving everything from our last class meeting, actually, I could literally just flip over here really quickly. We have this feedback system, right? Generically. And I mentioned that when that return mechanism when we have a plus sign, where we have that plus or minus option, that's giving us positive feedback. And when we have a minus sign, that would be taking into account a negative feedback system. Down here at the bottom of this page, we derived a mathematical relationship for our closed loop gain for a positive feedback system. What do you think the only change that's going to occur in our closed loop gain for a negative feedback system is going to be? Exactly right. That's going to flip the sign on that AOL times K term. So our closed loop gain, ACL, is going to be our open loop gain divided by 1 plus AOL times K. So what we can see from this expression is that our closed loop gain will always be smaller than our open loop gain, right? Because we have AOL divided by a term that is 1 plus AOL times a constant term, right? So if our open loop gain is very, very large, like in the case of an op amp, then this is actually going to reduce to 1 over K. So essentially, our gain will be set only by the presence of our feedback network. It will be essentially independent of the open loop gain of our system. This would actually be what's true for the ideal case, okay? So one of the consequences of this relationship is that in a negative feedback circuit, we are going to have what's called gain desensitivity. So remember from our last class meeting when I showed you that a change in the open loop gain by a factor of, I think it was 1%, yielded a change in the closed loop gain by over 90%. Now let's see what happens if we were to change our open loop gain by some amount and see what variance we see in our output. Okay. Find the right notes. Here we go. So let me just make a little note here. Gain desensitivity. Hope I spelled that right. Looks like I did. So let's say that we have a system whose open loop gain is 10 to the 4 and whose feedback factor K is 0.01. So in this particular case, our closed loop gain ACL would be 10 to the 4 multiplied by 1 plus 10 to the 4 times 0.01. And this would come out to be a gain, if my math is correct, which I believe it is, of 99.010. So we can see that our closed loop gain is significantly less than our open loop gain, right? We went from essentially a factor of 10 to the 4 to pretty much 10 to the 2, okay? So things are happening correctly. If we had a second case where our open loop gain were 9 times 10 to the 3, which would be a 10% reduction in open loop gain. That same feedback factor of 0.01, our closed loop gain in this case is going to wind up being 9,000 over 1 plus 9,000 times 0.01. And that comes out to be 98.901. So our difference in our closed loop gain, delta ACL in this case, would be, let's call this guy ACL1 and ACL2 so I don't have the same exact things here. ACL2 minus ACL1 over ACL1 times 100%, we only get a change of 0.11% from a 10% change in our open loop gain. So this is one of the real reasons why the overwhelming majority of op-amp circuits are negative feedback circuits. In a negative feedback system, it doesn't really matter that our very large open loop gain changes from device to device or component to component in a manufacturing run, because in a closed loop system, the gain is only going to decrease by some or change by some very small amount. So we're going to get very, very consistent results, even if we have quote unquote a bad op amp where the gain is lower than its typical value, or a quote unquote good op amp where the open loop gain is much higher than its typical value. Okay. So there are a couple of other properties of negative feedback. I'm not going to go into great detail for them today. When you get into your classes, particularly on transistor amplifiers where we're implementing feedback in those, we'll go into much, much greater detail. But this is kind of just supposed to be a surface level look, so I'm presently satisfied. All right, so let's look at a negative feedback op-amp circuit specifically. Sorry. There's my new notes that I made for today. All right. So this is the circuit that I want us to analyze. Okay. I've got my op amp here. I'm choosing to put my inverting input terminal on top. Here's VCC plus and VCC minus. I'm going to give myself negative feedback by connecting some resistor between my inverting input node and my output node. I'm going to call this resistor R2. I'm going to place a resistor R1 between ground and my inverting input node, and I'm going to choose to apply my input signal here. This will be Vin, just so that I have a fully defined system, so to speak. I'm also going to choose to include some arbitrary load resistance here, RL, and this will be our output voltage. Okay. So we're going to analyze this circuit the first time using the practical op-amp model. Okay. I want to figure out a few figures of merit. So we are going to let our input resistance for our op amp be 1 mega ohm, our output resistance for our op amp to be 25 ohms, and the open loop voltage gain for our op amp will be 10 to the 5 volts per volt. These are the values that I think we've been using for practically everything, because this is a pretty middle of the road op amp parameters. For our biasing network and all of that kind of good stuff, let's say that our resistor R1 is 5 kilo ohms, our resistor R2 is 10 kilo ohms, our load resistor is 10 kilo ohms. And just so that we get to use numbers and not wind up with a system of equations where we have only variables and have to solve it symbolically using a computer, I'm just going to say for now that we're going to treat our input voltage as 1 volt. Okay. Our ultimate goal with this example is to determine the following quantities. So the first thing that I want to know is simply my output voltage. Then I'm going to use that output voltage to determine my closed loop voltage gain, AVCL, which is just going to be the ratio of my output voltage of my system over the input voltage applied to my system. I want to figure out what my differential voltage is. So for what it's worth, we know that Vn is at the non-inverting input terminal. So our differential voltage is just going to be Vn minus the voltage at our inverting input node that I'm going to label as V minus, like so. That should have been C. D, I want us to find out what our input resistance for our system is. So this is going to be the input resistance with feedback. So we should actually see that the application of feedback changes the input and output resistance parameters of our system as a whole. The example that we're working here with our input signal applied at our inverting input terminal, we should see that the input resistance increases and our output resistance decreases. If we had our input applied on the inverting side, we should see that our input resistance decreases and our output resistance decreases. And why that happens will be explained much more in detail when you're truly looking at principles of feedback and all of that kind of stuff in your later classes. The last thing that I want us to find is the output resistance with feedback as well. Okay. So my goal in looking at all of these parameters for a practical op amp biased with standard value resistors and things like that is because I want us to analyze this circuit, get the results, and then see essentially how much error would be introduced if we use the ideal op amp model that we learned in circuits 1. Okay. So for determining the answers for parts A through C, we are just going to use our standard practical op amp model like we've been doing, right? So I'm going to start by drawing the op amp model itself. So let's just put that guy here. So here's my input resistance, which was 1 mega ohm in value. And I'm going to choose to put the positive polarity or the non-inverting terminal on bottom, just going to make the feedback easier to draw. So this node is going to be V plus, and this node will be V minus. That's making my differential voltage here with positive polarity on bottom, because the positive polarity terminal of VD is always at the non-inverting input node. I'm going to work on the output side of things over here. So here's my dependent source with a value of my open loop voltage gain times VD. Here's my output resistance of 25 ohms. And then here is my output voltage V out. Okay, so I've got my practical op-amp model in there. Now I'm going to start making the other connections. Okay, so between the output node and ground, I should have my load resistor RL. So that's going to look like a 10 kilo ohm resistor over here. Between my non-inverting input node and ground, I should have my input signal. So that's going to put a 1 volt source between these two nodes. Between my inverting input node and ground, I'm going to have that resistor R1. So this is a 5 kilo ohm resistor here. And then lastly, connecting my inverting input node to my output node, I'm going to have a 10 kilo ohm resistor. Like so. And what I'm going to do to solve this guy for at least these first 3 parameters is essentially just nodal analysis, okay? So I've got several nodes in this circuit, but realistically, only 2 of them are fully unknown quantities at present, right? So I hope pretty obviously, the voltage at the non-inverting input node is just 1 volts. The voltage at the inverting input node is an unknown quantity. So I'm going to wind up applying KCL at this node. The voltage at the node between my dependent voltage source and the 25 ohm resistor is an unknown quantity, but that's dependent on VD, which is in turn dependent on V minus. So I really won't need to do KCL there. So the other node that I'm going to have to apply KCL at is just my output node. So that'll be this current, and this current. Turn on scrolling, there we go. So applying KCL at the inverting input terminal node, I'm going to get V minus over 5 kilo ohms plus V minus minus 1 volt over 1 mega ohm plus V minus minus V out over 10 kilo ohms is equal to 0. So before I move on from here, does anybody have any questions about how I set up that KCL equation? All right. So over here on the right, so that we can still see the circuit, I'm going to go ahead and set up my KCL at V out equation. Okay. So starting with my current flowing to the left, I'm going to have V out minus AVOL times VD, where in this case, VD is just 1 volt minus V minus. and that will be divided by my 25 ohm resistor. Then I'll do the current flowing down through our load resistor. So that's just going to be V out over 10 kilo ohms. And lastly, I'll have the current flowing up through the feedback path. So that'll be V out minus V minus over 10 kilo ohms is equal to 0. So before I give you guys my results, let's make sure both of these equations seem okay to everybody. If you have any questions, by all means, please ask. Yes, sir.
Because the 1 mega ohm is so large, would that not just like kind of become 0?
So it's pretty much going to technically look like 0 amps of current is going to flow through that branch. I am intentionally not making that assumption here because I don't want to introduce our ideal op amp assumptions just yet until I show you that they are very, very valid. So you're 100% right. That current is going to look damn near 0. We are going to wind up calculating it in a minute or two, and it's going to be quite small. Okay, so if I solve this system of equations, what I wind up getting is that the voltage at my inverting input terminal comes out to be 0.9999699 volts. Very obviously, that is approximately 1, which means that there was approximately no current flowing through that large 1 mega ohm resistor, and V minus looks almost identical to V plus, but we're being formal here. Okay. I also get V out to be 2.9999093 volts. Obviously, that is approximately 3, but trying to illustrate what's going on here. Okay, so there's my answer for part A. I figured out what my output voltage is. I've made no assumptions about anything. I've simply used this model, plugged in the numbers. Okay. For part B of this problem, I was asked to find the closed loop voltage gain, which is just the ratio of V out to V in. Well, I chose V in to be 1 volt so that I could be lazy, because V out divided by 1 volt is just going to be 2.9999093 volts per volt. For part C, my differential voltage, VD, is going to be 1 volt minus what I got for V minus. And so when I did that math, I got 0.0000301 volts, or positive 30.1 microvolts. So before we get too much into the weeds of determining our system input resistance and system output resistance, let's think back on what we learned in circuits 1, okay? So what were the ideal op amp rules?
Zero current flowing into your.
So, yep, so no current would flow into or out of our input terminals. So we can see that even though we've used the practical op amp model, that is pretty close to happening here, right? How much current, just for what it's worth, let me label this current. So this would be the current flowing into our non-inverting input terminal. How could we determine that? We know VD. We know the resistor, so I feel pretty strongly we can just use Ohm's law, right? So just for what it's worth, the current flowing into our differential input would be VD over 1 mega ohm. So that would be 30.1 times 10 to the minus 6 volts divided by 1 times 10 to the positive 6 ohms gives me 30.1 pico amperes, 10 to the minus 12 amps. That's pretty damn close to zero, right? What was our second ideal op amp rule? Okay, so if the voltage at the inverting input terminal has to be equal to the voltage at the non-inverting input terminal, what would that say about our differential voltage VD for an ideal op amp? It's zero. We're getting 30.1 microvolts, which is, 6 orders of magnitude or 5 orders of magnitude smaller than our input signal. So that's pretty much happening here as well. So hopefully we are starting to see that this type of analysis is actually kind of a waste of our time if we know how to do ideal op amp analysis. But that's only going to be valid for negative feedback circuits. Okay. All right. So let's talk about part D here. Okay. So when I want to find the system input resistance, and this is your first time dealing with this type of concept, so I want to explain what we're going to do. You typically apply a test source across the input terminals of the system with the output terminals open circuited. So essentially, we are going to disconnect our load because we don't want that influencing the input resistance we see for our system as a whole. And then we're going to apply a test source at our input terminals, which I'm just going to make a 1 volt source because we can already analyze this circuit with a 1 volt source pretty easily, okay? So the circuit that we are going to be analyzing, I'll redraw it because you guys would probably be mad if I just copied and pasted. Would be something akin to this. So here's our 1 mega ohm of resistance. This is going to be our differential voltage VD. Here's AVOL times VD. So R out, but that should be just 25 ohms. I'm going to leave my output terminals open circuited. Okay. So no load resistance is applied here. I'm going to apply my test source across my input terminals. So I'm going to choose to make this a 1 volt test source, and I'm trying to find this current I test so that 1 volt over I test will give me the resistance I'm looking for. I have still a 5 kilo ohm resistor connected between my inverting input terminal and ground. So here's V minus, here's V plus, and then I have my 10 kilo ohm feedback resistor here. So essentially, I'm going to perform the exact same analysis that I did in the previous step to the circuit. The only change is I'm no longer going to have that V out over 10 kilo ohms term in my second KCL equation because I open circuited that 10 kilo ohm resistor, right? So just writing it down briefly, KCL at our inverting input node is going to look like V minus over 5 kilo ohms plus V minus minus 1 volt over 1 mega ohm plus V minus minus V out over 10 kilo ohms is equal to 0. KCL at my output node is going to look like V out minus AVOL, so 10 to the 5 times 1 volt minus V minus over 25 ohms. Plus V out minus V minus, excuse me, over 10 kilo ohms is equal to 0, and then I would solve this system. And when I solved it, I found that V minus in this case was 0.9999700 volts, and V out was 2.9999096 volts. So the input resistance that I'm looking for, lowercase rn, is just the ratio of our test voltage to our test current. Well, our test voltage is just 1 volt. Our test current is going to be 1 volt minus what we got for V minus over 1 mega ohm. And plugging in my value for V minus, I got 3.328 times 10 to the 10 ohms, or 33.28 giga ohms. So I had an increase of 3.328 times 10 to the 6% in my input resistance by applying negative feedback. What does that input resistance with feedback, how would we characterize that? Damn near infinite, right? We know that for an ideal op-amp circuit, we should be having effectively an infinite input impedance. Now let's calculate R out. So to determine the system output resistance, we typically apply a test source to the output terminals of the system while short circuiting the input terminals. So we're going to analyze this system a third time under these specific constraints. So let me just start redrawing my circuit yet again. Here's my 1 megaohm of op amp input resistance, my differential voltage VD. AVOL times VD, so 10 to the 5 VD. Here's my 25 ohms of output resistance. Here is my load resistor. So across my output terminals, I'm going to apply my test source. And I'm going to choose to have it be a 1 volt test source. And I'm now trying to find this current I test. And then the ratio of 1 volt to I test will be my system's output resistance. My input terminal needs to be short circuited. Still have a 1 kilo ohm resistor between my non-inverting input and ground. This is going to be 5 kilo ohm resistor. And I've still got my feedback resistor here of 10 kilo ohms. So since the voltage at my output terminal is now known, it's literally just 1 volt, I really only have to apply KCL at my inverting input node, and then I'll be able to sort everything out, right? So KCL at my inverting input, I'll get, sorry, let me label these. That's V plus, that's V minus. So I would have V minus over 5 kilo ohms plus V minus over 1 mega ohm, since V plus is grounded out, plus V minus minus 1 volt over 10 kilo ohms is equal to 0. And when I solve that for V minus, I got 0.322 volts. Knowing that voltage, I'm now going to solve for I out by applying KCL at this node. So I test. So I test is flowing in, this current's flowing out, this current's flowing out, and this current's flowing out. So I could say that I test is going to be equal to 1 volt over 10 kilo ohms plus 1 volt minus 10 to the 5 VD. What's VD now? Yeah, so it's just going to be negative V minus. So I'm just going to put this as plus V minus, and we could just substitute that number in, over 25 ohms. And then lastly, I would have 1 volt minus V minus over 10 kiloohms. And when I substitute in a value of 322 volts, I wound up getting a current of 1.329 times 10 to the 3 amperes. I want to be really, really clear here. If we apply the 1 volt source to the output terminals of a real op amp and we shorted out the inputs, we would definitely not see 1,000 amps flowing through the circuit. It would quite literally explode. This is just an analysis exercise to figure out what's going on. Essentially, all we're doing, by the way, is just finding the Thevenin resistance looking in and the Thevenin resistance looking into the output terminals of our network, okay? So from here, our system output resistance is just going to be the ratio of V test to I test. And we have 1 volt divided by 1.329 kiloamps. So I got a resistance of 7.525 times 10 to the minus 4 ohms, or 75 micro ohms of resistance. So that's pretty close to 0 output resistance, which is the ideal case for an op amp, okay? For what it's worth, this is a decrease in the output resistance of a factor of 3.328 times 10 to the 6%. So the input resistance went up by the exact same amount that the output resistance went down. That is a consequence of having negative feedback. For when we applied our input signal specifically to the non-inverting input terminal, okay? Okay, so let's revisit something from the second day of class, okay? And I think at this point, I'm literally just beating a dead horse, but we are going to conceptualize essentially why our ideal op amp conditions are infinite input impedance and 0 output impedance, okay? So on one of the very first days of class, I think it was the second day, I drew a circuit, something akin to this, where we had our signal to be amplified connected to some resistance RS, forming a practical voltage source. And this practical voltage source network was applied across the terminals of a black box amplifier. And then we went and we figured out that that black box amplifier could be represented by the practical amplifier circuit, right? Where we have our input resistance here, Rn. This is the input voltage of the amplifier block. Now I'm working on the output side, so we would have had AVOL times Vin. Here's our output resistance. Here's the output voltage of our amplifier. And then we had our load over here, RL, and this is the voltage drop across our load as a function of time. And I believe we stated that ideally, VL will be equal to a scaled version, so some amplification factor of V sig. So if I want VL to be exactly equal to some amplification factor times V sig, how could I make that happen? So let's start with the left-hand side or the input side, okay? So I want to make Vn be exactly equal to V sig. How could I do that? So let me phrase it in a slightly different way, okay? I believe that the input side of that circuit is a voltage divider, okay? So the voltage that I have labeled as Vn, and I'll put it as a function of time here, could be expressed as V sig as a function of time multiplied by Rn over Rs plus Rn. That's literally just using voltage division. Everybody okay with that? What value must Rn have to make Vn equal to V sig? Anybody? Say what you're thinking, Austin. You've got a smirk on your face, so I feel like you've got it. Nope. Okay. Sorry for picking on you. Josh, what is your immediate thought? So if I want Vn to be equal to V sig, then that ratio of resistances Rn over Rs plus Rn needs to effectively be 1, right? How does that happen? So if Rs, let's throw numbers at this thing. Let's say that Rs is 50 ohms. And I want Rn over Rn plus Rs to be as close to 1 as possible. Do I need to make that input resistance larger than Rs or smaller than Rs? Larger. And the larger I make it, the closer that ratio gets to 1. So in an ideal case, Rn needs to be an open circuit, and then Vn will be exactly equal to V sig, right? There will be no voltage drop across the resistor Rs. There won't be any current flowing through it. It's not part of a closed current carrying network, okay? So Rn has to be equal to infinity for Vn to be equal to V sig. Okay. Now let's look at the output side, okay? So I want VL to be equal to AVOL times Vn, okay? But I've got this pesky voltage divider where I'm going to have AVOL times Vn multiplied by RL over R out plus RL. So what value does R out have to make that ratio of resistances 1?
Basically zero.
Zero, exactly right. So in our ideal case, we need R out to be 0 ohms for VL to be equal to AVOL times VN. If I put both of these things together, then I have a situation where the voltage drop across my load is exactly a scaled version of the voltage drop applied at my signal source, okay? So in the ideal case, R in has to be infinity, R out has to be 0, and this isn't intuitively obvious from what we've talked about here, but if we go way back to the beginning of this lecture, and this relationship right here, in a negative feedback system, our open loop gain needs to be infinitely large in order for our closed loop feedback to be completely determined by our feedback network. So the third constraint is that for an ideal op amp is that our open loop gain is infinitely large. So let's look at our circuit that we analyzed a couple of moments ago under these constraints, okay? And I'm still going to effectively use the practical op amp model in this case. We'll get away from it literally the beginning of next class. But for now, we're going to use the practical op amp model with those ideal parameters, okay? So that would look something like this. So I've got an open circuit here. So effectively, I've got Rn is equal to infinity. Here's V plus, here's V minus. I've got plus minus AVOL, which in this case is going to be infinity times VD. I've got a short circuit where R out was supposed to be. So this is my implementation of R out is equal to 0. There's V out. Here's my load resistor. And I'll make this a 10 kilo ohm resistor. Let's see, I'm applying my input voltage of 1 volt here. I've got my five kilo ohm resistor here. And my 10 kilo ohm resistor here, okay, for my feedback resistor. So for at least one of our ideal op amp rules, it should be very easy to figure out where it comes from, right? So what's the current flowing into the input terminals of my op amp? 0, because there's an open circuit there, right? So this is literally where ideal op amp rule number 1 comes from. Okay. For my second ideal op amp rule, it's a little bit harder to sort out. Okay. So my output voltage, V out, is equal to infinity times my differential input voltage. Okay. I can rearrange that guy to say that my differential input voltage must then be equal to whatever my output voltage happens to be divided by infinity. Well, what happens when I divide any number by infinity? It's 0. So this is where that second ideal op amp rule comes from. This is called the voltage constraint rule, right? So if VD has to be equal to 0 volts for an ideal op amp, then that means the voltage that we have at our node V plus must be exactly equal to the voltage that we have at our node V minus. So quite obviously here, the voltage at our node V plus is 1 volt. So our nodal voltage here is 1 volt. And now we can simply apply KCL at this node, adding this current and this current together to solve for V out, right? So we would have 1 volt minus 0 volts over 5 kiloohms plus 1 volt minus V out over 10 kiloohms is equal to 0. Solving this guy, we would wind up getting V out is equal to exactly 3 volts. And as it turns out, our voltage gain, AVCL in this case, is then V out over V in is 3 volts, which is literally just the ratio of 1 plus R2 over R1. So our voltage gain, our closed loop voltage gain, is defined only by our feedback network, which is exactly what we should expect for an ideal op amp system. So I'm essentially out of time here, but what I want you guys to draw from this lecture is that when we analyzed our original circuit using our practical op amp model, sorry, let me go back up here. We got, for all intents and purposes, the exact same results that we got using the ideal op amp model. So essentially, any time that we have a negative feedback op amp circuit specifically, we can just use the ideal op amp model and we will introduce an incredibly small amount of error. So I'm going to put a homework assignment up about this where I want you to specifically find that error, but it's going to be on the order of 1% tops kind of thing, even for very poorly designed op amps. So I'm talking about open loop gains of 1,000 or something like that, and output resistances of kiloohms. It's still only going to introduce 1% or 2% of error.